Today's video is all about molecular and empirical formulas. How you find them is what we're learning about. So a molecular formula, which a lot of times you'll see me abbreviate as MF, is a group of element symbols with subscripts which represent the actual composition of a molecule. It shows the actual number of each atom found in a specific molecule, not simplified. So you could have C6H12O6. Those are all divisible by 6 technically, but we want to know the actual composition. Meanwhile, the empirical formula, abbreviated EF, shows the simplest whole number ratio for those elements in a compound. So it's just essentially the simplified version of the molecular formula. So C6H12O6 just would become CH2O because we're simplifying it down. To find the empirical formula, you determine the largest common denominator of the subscripts of the molecular formula and just divide everything down. Sometimes your empirical formula will equal your molecular formula, especially in ionic compounds because we're supposed to reduce those down anyway. So sometimes it works out, sometimes it doesn't. All right, so you've been told that your molecular formula is essentially the real formula, the non-simplified formula. Well, the empirical formula is our simplified formula. So H2O, can that be simplified down to anything else? So we have 2 H's and 1 O. That's not divisible by anything, which means our empirical formula is the same. This is one of those cases where it works out. So H2O is the empirical and molecular formula. What about number 2? H2O2. Do those have anything in common? They have 2 H's, 2 oxygens. So those are both divisible by 2, which means our empirical formula is just HO. Got the hang of it? I want you to pause this video and try 3 through 6 on your own. Come back when you have your answers. All right, C6H12O6 reduces down to CH2O. CH4 stays as CH4. C2H6 becomes CH3. And C4H9 is the empirical formula for C8H18. Pretty simple, right? Feel like if I give you a molecular formula, you can come up with the empirical formula. No problem. That's the easy part of today's lesson. So let's talk about how we determine that molecular formula in the first place, because you're not always just going to be given the molecular formula. You have to know how to find those too. So the steps to determine the molecular formula when you are given the empirical formula and the molar mass. That's what we're going to be learning about. So first, you're going to determine the molar mass of your empirical formula. Just like we've determined molar mass before, that's all you're doing. You take the empirical formula that you were given and find the molar mass for it. You're going to divide the molar mass of the MF, which you would have been given in the problem, by the molar mass for the EF, which you calculated in step 1. Just showing you molar mass of MF divided by molar mass of EF should equal a multiple of some kind. You might have to round it up to a whole number, but we're talking like 1.99 rounds up to 2. And then you're going to multiply the subscripts of the EF, once again you were given that in the problem, by whatever multiple you got in number 2 to get your molecular formula. Let's work some examples together because I know that can sound a little weird, but once you see it in practice, you can do this. All right, so you were asked what is the molecular formula for a compound that has a molar mass of 98.21 grams per mole and an empirical formula of CH2. So for step number 1, we are going to calculate the molar mass of CH2, which we got to be 14.03. Then we're going to divide it by the molar mass that we were given in the problem, 98.21, and that works out to 7. So that means we're going to multiply our entire empirical formula by 7, so C7H14. All right. Let's try a second one. What is the molecular formula for a compound that has a molar mass of 120.02 grams per mole and an empirical formula of CO3? I want you to pause this video and try this one on your own. Come back when you're done. Okay, so just like before, we calculate our molar mass of CO3 and got 60.01. We divide 120.02 by 60.01 to get our multiple of 2. And then we multiply our formula, C2O6. Pretty straightforward. Now the trickier one is determining the empirical formula. So given the percent composition of each element in the compound, you can determine what the empirical formula is. So let's look at what our steps to determine the empirical formula are. There's going to be more steps than for our molecular formula. So you're going to use the mass given. There will be, or if no mass is given, you're going to assume that it's exactly 100 grams of a substance. So you're going to change that percent sign essentially to a gram sign. So you're going to be given your percent composition. If you are told a number of grams, you're going to have to figure out what percent each of those are. If you are not given a number of grams, you just say, if I have 50%, that means that's 50 grams. Pretty straightforward. You're going to convert mass into moles, so combining what we've learned in previous videos of each element by dividing the mass by the molar mass of the atom, and this will give you the moles of the atom. You're going to want to keep 4 decimal places. You're going to compare the mole quantities, find the ratio, by dividing all the moles by whatever the smallest number of moles is. This step should produce a whole number. Like I said, you might end up with like 1.99 and that rounds up to 2, but if you end up with like 1.5, you're going to have to multiply everything by 2 to get them all to whole numbers. And then you're going to use the ratios from step 3 as your subscripts. All right, let's work through an example together because I know this can be a little overwhelming. So you were asked to determine the empirical formula for a compound with the following composition: 40% carbon, 72% hydrogen, and 53.28% oxygen. 40% carbon, 6.72% hydrogen, and 53.28% oxygen. So step 1, we're just going to assume there is exactly 100 grams of each substance. So since combining all percentages adds up to 100%, this means we have 40 grams of carbon, 6.72 grams of hydrogen, and 53.28 will be oxygen. So in step 2, we're going to convert the mass into moles of each element by dividing the mass by the molar mass of the atom. So we take 40 grams of carbon. The molar mass of carbon is 12.01 according to the periodic table. We divide to get 3.3305. 6.72 grams of hydrogen divided by the molar mass, 1.01, gets us 6.6535. 53.29 grams of oxygen divided by 16, because that's the mass on the periodic table, gets us 3.3306 moles of oxygen. For step 3, you're going to compare the mole quantities by dividing all the moles by the smallest number of moles. So in this case, the smallest number was 3.3305. So we divide each of our numbers by that. When you do that with carbon, you get 1. When you do that with hydrogen, you get 1.996, which rounds to 2. When you do that with oxygen, you're going to get 1. And you're going to use those ratios from step 3 as which means we have CH2O. So we have found our empirical formula, the most reduced one. Now we can use the empirical formula to calculate the molecular formula. So after determining the empirical formula is CH2O, suppose the molar mass of the molecular formula is 180 grams per mole. What is the molecular formula? So we are going to divide the molar mass of the molecular formula by the molar mass of the empirical formula. So our molar mass of the molecular formula was given to us. The molar mass of the empirical formula we calculate to be 30.03. That equals 6. So in order to find the molecular formula, we just multiply the whole thing by 6, giving us C6H12O6, also known as glucose. So if you do not get whole numbers when you divide by the smallest number of moles, and you get a number that ends in 0.5, you're going to simply multiply all the elements by 2, because 0.5 is really 1/2. If you didn't get a whole number and you get a decimal other than 5, you messed up somewhere. You're either going to basically get a whole number or you're going to basically get 0.5. If you end up with 0.72, you have messed up somewhere and you need to go back and check your work. So why do we want whole numbers? We want whole numbers because our formulas only exist in whole numbers. When we were doing ionic and covalent naming, you never got C.25 H.75, everything is in a whole number because you can't have part of an atom. You have a whole atom, 2 whole atoms, 3 whole atoms. You can't have part of an atom, so we need whole numbers. Let's work another example together before I set you loose on your own. So I want you to calculate the empirical formula of a compound containing 38.67% carbon, 16.22% hydrogen, and 45.11% nitrogen. So step 1, we're going to assume 100 grams of each sample, which means we have 38.67 grams of carbon, 16.22 grams of hydrogen, and 45.11 grams of nitrogen. So far, so good. Step 2, we're going to convert each of the mass into moles. So we take those masses that we got in step 1, and we're going to divide them by the molar mass of each element. These numbers came straight off the periodic table, and once we do that, we get our answers. 3.220, 16.09, 3.219. We're going to compare our mole quantities and divide each one by the smallest number. So in that case, it was 3.219. So we divide each of our answers by 3.219 to get 1.003 carbon, which is essentially 1, 4.998 hydrogen, which is essentially 5, and 1 nitrogen, which works out to 1 nitrogen. So that means our ratio of carbon to hydrogen to nitrogen is 1:5:1, meaning our empirical formula is CH5N. So after determining the EF is CH5N, suppose the molar mass of this compound is 93.21 grams per mole. So we're going to divide the molar mass by the EF mass. So we take our mass we are given in the problem. We're going to divide it by 31.07. That is the molar mass of CH5N. And that's going to get us a number, roughly 3. So that means it is 3 times as much. So we multiply the whole thing by 3 to get C3H15N3. I know it's a lot of steps, but if you just learn the steps, you can solve any problem there is out there. All right, now's the time to practice on your own without me going through it step by step. So I want you to pause this video and figure out a substance is 41.87% carbon, 2.35% hydrogen, and 55.78% oxygen. I want you to tell me what is the empirical formula. Pause this video, come back when you're done. All right. So if you did everything correctly, so your ratio worked out to 1.5 to 1 to 1.5, which aren't whole numbers. But before you say, I must have did this wrong and I need to start over again, what do? That's right, we talked about it. You multiply everything by 2. So that gets us C3H2O3 as our empirical formula. How'd you do? If you got this one wrong, I recommend rewinding the video and watching it over again. One more example to try on your own to see how you're doing. You were told that caffeine is 49.48% carbon, 5.15% hydrogen, and 28.87% nitrogen, and 16.49% oxygen. You are asked to find the empirical formula. Pause this video, come back when you're done. All right. You should have gotten an answer of C4H5N2O. Interestingly, that is the empirical formula for both caffeine and theobromide. And if you're thinking, I know what caffeine is, Ms. Hinkson, but I don't know what theobromine is, it is the primary component of chocolate. So that is the empirical formula for both caffeine and chocolate. Now, they both have different molecular formulas, but they have the same empirical formula. Little known thing for you. All right, come to class tomorrow, ready to practice empirical and molecular formulas.